Okay, here we're going to introduce a technique that very quickly identifies the net acceleration, A. It is called the systems approach, and I see it frequently used in online videos recommended for high school AP physics. The systems approach is a powerful and important technique. In fact, it is quite useful for problems where pulleys are mounted on an inclined plane, or pulley problems involving 2 or more pulleys or 3 or more masses. The technique is powerful because it reduces the number of forces that must be considered. Although very powerful, I recommend this technique be used only after a novice learner has mastered the free body diagram approach for a 2-body pulley system. So, our pulley problem begins, as before, with M1 greater than M2. The next step comes from a deeper understanding of the magic of Newton's second law. Stated in words, Newton's second law tells us that the net acceleration of a system results from the net external force acting on the system. Implicit in this idea is that the net external force derives from the sum of the external forces acting on the system. The key then becomes on how we define what constitutes the system, and we are free to define our system as broadly as we like. So in the case of the pulley system, we will define the system as the 2 masses and the string. Now, to make this a little more intuitively obvious, I've redrawn the masses and the string along a single line on the upper right-hand side of the slide. I'm not suggesting they operate this way. For now, I'm simply redrawing the diagram to make the system concept a little easier to visualize. In a moment, we'll show how this unbending of the system and drawing it in a line also helps us to understand how to interpret the signs of the forces involved. I'll come back to this idea in a moment. Now, since we are free to identify our system as broadly as we desire, I'm drawing a dashed red box around my defined system. This system includes both masses and the string. And conceptually, this makes sense because the masses and the string do move together. And we showed in a previous video that the acceleration of the masses are the same. This is the result of our assumption that the string is inextensible or non-stretching. And although we didn't prove it, it is also true that the string accelerates at the same rate as the masses. And because all objects, that is M1, M2, and the string, are all accelerating at the same rate, we can define these objects as our system. Now, with this definition of system, we'll identify all the external forces acting on the system. Forces acting on the outside of this boundary are called external forces. Forces on objects within our red box boundary are called internal forces. In this example, there are 2 external forces. These are the weights of mass 1 and mass 2, which I've indicated as acting on the contents of our red box. In addition, there are 2 internal forces, which are the tensions of the string. We'll come back to the internal forces shortly. Next, I need a direction for the net acceleration of our system. Remember, our system is the contents within the red box. Based on our intuition of the pulley's behavior and our given assumption that M1 is greater than M2, I've assumed that the acceleration will be to the left. This is the subtle advantage of redrawing the system in a straight line. It helps us see that the problem is really one of a single dimension, and it allows us to more easily assign or provide signs to the external forces involved in moving our system. Now, to do this, we need a sign convention. In this instance, I'm selecting forces that move the system to the left as negative. And since I'm assuming the system is moving, that is accelerating to the left because M1 is greater than M2, then I'll also assume the net acceleration of the system is negative. Now, before we start writing equations, I want to avoid my own hand wave and explore a little further why our unbending approach creates problems for the novice. So, to show how we haven't lost any generality, we can also view the system as it exists on the pulley without straightening the pulley system out. Here then, shown on the left, we have 2 external forces acting on the pulley. These are the weights of the pulley, and they both point down, as we've seen many times in the past 3 videos. What often confuses novice learners is that since both weight forces point down, these forces should be given the same sign, and they aren't. they are given different signs, as we see in a moment. And this is the reason I think this approach should be delayed until Newton's second law is mastered with the use of two free body diagrams. So, what is really going on is that our systems technique is really using a rotational sign convention as we discussed in the previous slide. Now, to be clear, by choosing left as negative in my straight line approach, I've also chosen forces causing counterclockwise rotations to be negative. This is opposite of the sign convention that is usually used where counterclockwise rotations are positive. This is okay as long as we are consistent with our choice of sign convention when solving our problem. In fact, the reason I've chosen this non-typical sign convention is I want to demonstrate that it does work. One final point. The advantage of the rotational sign convention is that it does make it easier to realize that the two downward forces are actually competing and therefore should be given different signs. One downwards force is causing a counterclockwise rotation and the other is causing a clockwise rotation. So, let's return to our straight line drawing and write some equations for it using Newton's second law. Because m1 times g is driving an acceleration to the left, and because we've chosen the sign convention that left is negative, we give this force a minus sign. And because the weight of m2 is driving our system to the right, according to our sign convention, it is assigned a positive sign. It is the interplay of these two forces that creates our net acceleration. Mathematically, we capture this interplay by the difference of these forces. And this difference results in the net acceleration of our system. Since we assumed our net acceleration is to the left, again because m1 is greater than m2, we initially assumed it was moving to the left. And so it is also given a negative sign. Now keep in mind, a represents the net acceleration of the system. And the mass term in front of a is the mass of the system, which is m1 plus m2. Now, we can readily solve for a. This is the beauty of the systems approach. It makes the algebra very straightforward and allows the acceleration to be solved quickly. And we see that we have the exact same solution as we had in video 3, where the numerator is m1 minus m2. Since m1 is assumed to be larger than m2, the numerator is positive, and therefore the sign of the net acceleration is also positive. That means that our assumed directions to the left or counterclockwise in a rotation sense were correct. So, what about our internal forces? Well, the beauty of the systems approach is that they can be ignored. That is, the two tensions are equal and in opposite directions, so they cancel. Mathematically, we saw this canceling occur when we added the two equations to solve for the acceleration of a in a previous video. That is, the t terms don't appear in our answer. The stumbling block for novice learners is that the tension forces act on different objects. In this example, one tension is acting on m1 and the other tension force is acting on m2. Their net effect, however, is that they cancel, and internal forces always cancel. Now, warning, the following thought is a partial hand wave. The reason internal forces cancel is that they always come in action and reaction pairs, as a result of Newton's third law. As a result, these forces can be grouped together in such a way they always cancel. In our example, the string on m1 with tension, the string pulls on m1 with tension T, and m1 pulls back on the string with the same magnitude but in the opposite direction. This is Newton's third law. The same occurs with mass 2. Mathematically, when added together, these four forces canceled, and this is the hand wave. I have not shown rigorously how this cancellation occurs. If this is not clear, don't be alarmed. This is a subtlety that merits its own video. What is important to take away here is the fact that only forces external to the system cause the system to move. Now, in this last example, I wanted to replay the systems approach, but make the assumption that our net acceleration of the system is to the right. That is, our sign conventions are the same, and our given m1 is greater than m2 is also the same. I want to show what happens if our assumed direction of the system is wrong. That is, our intuition about how the system will move is backwards. This is an interesting exercise because it provides a practical counterpoint to the majority of online and in-class demonstrations that always seem to show the correct answer being derived. And somehow, when we're home doing problems, we often encounter the contrary result. So what I want to show is how to interpret your answer when your solution provides a negative result. Applying Newton's second law to our system, we see that m1 times g is to the left. Using our sign convention, we give this force a negative sign. Similarly, m2 times g is positive. Now on the right-hand side, we again have this system mass as m1 plus m2. All of this was exactly as it was in the last slide. Now, a is positive because we assumed the net acceleration of the system to be to the right. When we solve our equation, we see that the numerator is m2 minus m1. This is exactly the solution that Survey got. Now, let's consider our given. That is, let's consider that we are told m1 is greater than m2. This means that our acceleration is negative since m2 minus m1 is a negative number when m1 is greater than m2. It is implicitly negative in the context of our givens or knowns. This means that our direction for the system is opposite to what we initially assumed it to be. Since we assumed that it was moving to the right, and since we found our solution to be a negative result, we can then conclude that our system is moving to the left, opposite to what we assumed. The sign of our result tells us how to interpret the correctness of our original assumed directions.